don't live in New York City, you may be impressed that when you get on a subway, everybody pulls out a phone and does their internet checking. So, to avoid that here, there's a special arrangement for the workshop to gain access to the Wi-Fi here at Hunter. I have hidden it behind the screen here. The username is math workshop, MATHWKSHP. I wrote that here. You don't have to memorize it. And there's a password. I'm even going to try and describe it. But after all the talks, you're welcome to come up, look at it. You can log on, check email, do all those kinds of things. Meanwhile, we have somebody formerly with us, and now, what was the phrase? Reassociated.
Retired.
Because Carlos has come back, at least for the talk, who will talk to us about projectively integrable linear difference equations in Galois. Arreche.
I'd like to begin by thanking our fearless organizers for putting this together, and it's a pleasure to be here again. Hopefully there will be many more floating workshops. It's always nice to be one of the dearly departed. So I should say too, this is all joint work with Michael Singer. So let me begin. So this will be about a kind of Galois theory. I thought I should have at least one slide that doesn't mention Galois theory, so I can convince you that this kind of it has applications to other areas where people care about things. So here are two sequences that people study in automata theory. One is a Baum-Swift sequence, and you define an to be 1 if every block of zeros in the binary representation of n has even length. Otherwise, an is 0. And then, given a nice sequence that you care about, you can just write down this form power series. It's called.
Why is that sequence studied?
Pardon me?
Why do people study that sequence?
Apparently, it describes certain kinds of finite state automata. I have to say, I apologize to any automaticians we have in the audience. I don't know very much about this. I just wanted to mention things that have names that you can look up later. Here's another sequence that people care about for some reason, and here's the description. And so it's a classical problem if you're given a generating function for some sequence that you're interested in. If you're able to tell that the power series happens to be an algebraic function, or maybe definite, or differential algebraic, that tells you things about your sequence. So not for the ones that I wrote down, but there's a way to write down a sequence that somehow captures certain kinds of walks in the plane. And when you write down this generating function, people are sometimes able to prove that the generating function is either algebraic or definite, and that gives you really good bounds on the growth of the sequence. That's not interesting here because all the elements of the sequence are either 0 or 1 or 1 minus 1. You know pretty well that they don't grow at all. But these kinds of facts still tell you interesting things about your sequence. And so here's a kind of like a kind of result that you can show. It turns out that these two sequences are differentially transcendental over the rational functions. And so this is the kind of result that we're interested in obtaining with the technology that I'll describe today. So I'll tell you a little bit about one way to go about proving this kind of result. It turns out that the generating functions satisfy linear difference equations over the rational functions. So there's a Galois theory describing those, and the Galois theory associates to the equation a Galois group that captures the algebraic relations among the solutions to your equation. And saying that there are few relations among the solutions, maybe saying something like the solution is transcendental, that's essentially the same as saying that the Galois group is large in some sense. Now there's also a difference-differential Galois theory for difference equations that tells you in the same way it tries to capture the differential algebraic relations among the solutions to the difference equation. And similarly saying that there are very few differential algebraic relations is the same as saying that the Galois group is large in some sense. And so I'll present the theoretical results that Dreyfus, Ardoin, and Rock used to prove their result. And then I'll describe some generalizations of the work by Michael Singer and myself. But for all of them, even the ones that look technical, this is what they're trying to get at. All these results, these tools, will allow you to deduce in certain cases that the differential Galois group is very large, just from the knowledge of the difference Galois group. So you'll be able to get a lot more knowledge for free. I should also say that when I say that the difference Galois group is large and that the differential group is large, these are different senses of large, but they'll be very precise.
So are you making some kind of assertion that you can't satisfy both the difference and the differential equation?
Yeah, that's almost true, except for examples that we completely understand. That's the reason why I get this kind of result. A solution to a difference equation really doesn't want to satisfy a differential equation also, and if it does, it's incredibly special. Okay, so I'll briefly describe the difference Galois theory that maybe everyone here knows, but we're watching at home. So you begin with a base field that's equipped with a automorphism, sigma, and if you assume that the sigma invariants are algebraically closed, then you're given a difference equation over your field. Then associated to such a difference system is a sigma Picard-Bessel ring, which plays a role in this Galois theory of the splitting field in classical Galois theory. Since it has as many solutions to the equation as you could possibly have, and it's minimal with respect to that property. So it only contains the solutions and 1 over the determinant of this so-called solution matrix. And the requirement that it has no constants, it just makes the Galois theory run. So this object exists, and you define the sigma Galois group as a group of k-algebra automorphism of this Picard-Bessel ring that commute with sigma. So the Galois group contains all the matrices that respect the algebraic relations among the solutions and also the action of sigma. You can show that this abstract group of automorphisms, when you see what it does to the fundamental solution matrix by acting entry-wise, you find that it transforms it by multiplication on the right by a matrix of constants, and this gives you an embedding of your Galois group inside the LNC, and the image is actually a linear algebraic group. So it's got all this algebraic group structure that's really useful. So that's the abstract theory. The main examples that we'll care about for most of the results today are these three. So one, the shift case, your base field is rational functions, and sigma which replaces x with x plus 1. The other one side, it's usually called Q difference, but we're trying to start a trend, and the trend exists already. We'll try to reinforce it to call them Q dilation operators instead. But anyway, this is what it is. Sigma just replaces x with Qx. And you can also consider this other case, where a Mahler operator that replaces x with x to the p. this is the difference operator that's behind the two sequences I described at the beginning. And there's a little technical annoyance in that if you let sigma in this way only on the rational functions, it wouldn't be an automorphism anymore. It would be like a self-betting. And you could, I think, Michael Bigmer has a different Galois theory that's more geometric, and only having an endomorphism is okay. But to apply the version of the differential Galois theory that Haruan and Ziegler developed, I really want to work over with an endomorphism. So now the differential Galois theory for difference equations is very similar. Now you assume that your base field is equipped with an automorphism as well as a derivation, and you demand that they commute. Now, someone gives you, again, just a linear difference equation. You can associate sigma delta Picarescu ring to it, provided that the sigma invariants are differentially closed. So again, maybe in many cases you can get rid of this assumption, but I'll show you when I need it. So this Picarescu ring in the theory plays the same role as the old one in just classical difference Galois theory. You have as many solutions as you could possibly have, and R is the smallest differential ring that contains all the solutions. So it's differentially generated now by the entries of the fundamental solution index. You write down the definition for the Galois group that you would expect. Now you want K-algebra automorphisms that not only respect the action of sigma, but also the action of delta. So you're looking for matrices that kind of respect the differential structure of the difference structure. And the same argument that I didn't describe before makes now the Galois group into a differential algebraic subgroup of GLM. So it's a linear differential algebraic group in the sense of Katzi and Kolchak, and we have a lot of results about this. So the main examples that we care about are the same ones, but now I have to tell you what the differential structure is. So in this case, the usual derivative commutes with the shift. In the Q case, you have to take this other one, x to the x commutes with that sigma. And in the Mahler case, now it's even a little bit more annoying because to have a derivation that commutes with this sigma, you have to throw in this log. I'll just say about that it's only a little bit annoying when you're trying to prove things, but it's not a very big deal. Often, in principle, you need to find a solution to an equation over this field, and you can use standard descent arguments to come down to only answering questions over C of x. And it's also conceivable that you don't really need sigma and delta to commute. Here you can show that they essentially commute up to a constant if you didn't have the log, and it's conceivable that you could develop the Galois theory in that kind of generality, but this will work. Okay, so these are the base fields that I care about with their difference differential structures. And whenever I want to apply the difference differential Galois theory, I'm going to consider my equations as defined over a larger field where I replace the sigma invariance being the complex numbers with some differential closure of the complex numbers. So I'm going to write H for the classical difference Galois group, that's a linear algebraic group. And then I'll write G for the difference differential Galois group. So here are some results of Dreyfus and Rock, the Galois theoretic tools behind their hypertranscendence results. So the first one says that if the difference Galois group is large in the sense that it contains SLN, then the differential Galois group contains SLN of the whole differential closed field. Now this should have appeared in a previous slide, but it didn't. The only Zariski dense subgroups of SLN, for example, or a simple algebraic group, is either the C points of the group, or of the conjugation, the differentially constant points of the very same group. So if your algebraic group is simple and you know that the differential group is dense in there, you only have two choices. You have to decide if it's differentially constant or the full SLN. And if you know that the Galois group contains the full SLN, it's not difficult to then show hypertranscendence. And this is in fact what they do in the examples. Those examples satisfy the Mahler equation, and Rob had shown previously that the classical difference Galois group contains SLN, and now they just apply this and show that the differential group has to be large as well, so the solutions are hypertranscendental. They have a similar result for two difference equations. It's a little bit more technical. You assume that the derived subgroup of the connected component of the difference Galois group is irreducible and almost simple. So this is what it means to be large for the difference Galois group in this case. Then you get a similar statement that the differential group has to contain all the C points of this large group, as opposed to maybe just the differentially constant points, which was the only other option.
So to what extent do these theorems depend on the arithmetic of C of X?
A lot. Yeah, even looking at equations over C of X with this C changes the results. Yeah. So I should say that this other result, they also have results for Q difference equations. They can show that like certain classes of generalized cube hypergeometric series are differentially transcendental by applying this other result instead, together with knowledge of what the classical difference Galois group is for the equations they look at. Very similar results, and they all come from this principle, knowing the different Galois group and some kind of tool that tells you that the differential group has to be big. So what we've shown, we're still writing this up, but in the shift, Q dilation, or Mahler setting, all of them, if you know that the difference Galois group contains a semi-simple group, then the differential group will contain all the C points of that semi-simple group too, as opposed to maybe having like some simple factors with differential constant. That can happen. They all have to contain all the C points, and that's kind of surprising. And so this allows you to carry out very similar arguments in many more cases. It's not just this sort of strange condition or even containing SLN. It really generalizes these two situations. I should say that in the shift case, all the results coming from here are new, because they only handle the Q dilation case and the Mahler case. To say that the way we go about proving this is by focusing on the notion of integrability. It turns out that if you know for a simple Galois group, differential difference Galois group, like I just said, if you know that the difference differential group is dense in say a simple algebraic group, then the only options for the differential group are all the C points or the constant points, and that choice is controlled by whether the equation is integrable or not. So in trying to understand the semi-simple differential Galois theory, it makes sense to really study integrability. So this is what it is. You start from a difference equation, and you say that it's integrable if either the Galois group is contained in the differentially constant points of the conjugation. Asking this is the same as asking for another matrix that satisfies this equation. and this condition is exactly what you need on B to have this difference differential system be compatible. So somehow have the actions of sigma and delta commute acting on the unknown matrix Y. Okay? So that's what it means to be integrable. There's a related, more general notion said that it's projectively integrable. These two are equivalent as well. In terms of the group, it has to be conjugate to a subgroup of this, which maybe makes sense to call them projectively constant, because they're, the image of this in PGLN is actually in the constant points of PGL. But anyway, this is what it means for the group. And it turns out that this is equivalent to the existence of a matrix over the ground field that satisfies this kind of twisted version of the usual integrability equation. So what we've shown is that you again let H be the sigma Galois group and G be the sigma delta Galois group. In any one of these three cases of interest, if the equation is integrable, then the difference Galois group has to be abelian, and then the differential one. And that, like to pause for a moment to convince you that that's very strange, because the difference Galois theory, in principle, it doesn't yet care about differential anything. And this result is saying that it's allowing me to go back from the differential Galois theory to say something about this difference Galois theory. The existence of a matrix B satisfying this stuff kind of is enough to force the difference Galois group to be abelian. Usually you go the other way. And then you can push this a little more and say that if the system is only projectively integrable, then the groups are solvable, and in fact the connected components are abelian too.
Carlos, are there counterexamples to these other settings, other kinds of operators?
Pardon me?
So you could put examples of automorphisms.
Yeah.
So what happens? Other counterexamples if you go more general?
Oh, quite possibly. I will describe what sort of a proof outline for this, and this all relies on a quite strong, I think, recent result of Schaefke and that tells you that very special things happen in these situations, and some others that I'll mention later when I talk about a discrete parameter instead. But yeah, for more general fields or more general sigmas, I have no idea what happens or what to expect.
In your definition of integrable, it sounds familiar to me if the ambient group is SLN. So you can get the same results when you just assume GLN? Go back to the definition.
Sure.
Integral. I immediately moved to SLN.
Oh, where, here? Or?
No, in the definition. But so you work in GLN, not you don't always work in SLN.
Right.
There is we get subgroups of GLN. Ah, that's very nice.
Yeah. Yeah, and that's actually something. That's something interesting about the difference Galois theory. In the differential setting, there's a standard trick that kind of allows you to relate any old equation that you start from to an equation with group in SLN. And the same thing doesn't quite work in the difference setting. You can sort of move symbols around. The problem has to do with taking nth roots of like a rational function and wanting that to have a different structure.
Right.
And possibly having like a field that's got infinite degree over the ground. It's maybe not a big deal, but I thought it was troublesome. Okay, so once you know this, this comes out relatively easily. The idea is that if the difference Galois group contains a semi-simple group, then if the if there was only a proper differential and then subgroup of this containing G, something would have to be integrable, and that factor would have to be abelian, but it's not. So that's where that came from. And I'd like to give you an idea of how this is proved, because because I get to it's conceptually simple.
Carlos, could you explain again how writing down a certain equation is related to projective?
Oh, for the definition of projective integrability?
Yeah. Could you explain the certain equation? How it's related?
Interesting.
Yeah. So what this equation, having a b in the rational in the ground field satisfying this equation, what it means is that let me call this one b prime. The existence of this b makes it so that there is a b prime living not in the ground field anymore, but in GLN of k adjoin some eta, where eta satisfies a first order equation related to the determinant of the group. And so you do achieve integrability, but only after taking the determinant and looking at the smaller Galois group over that field.
But you might as well adjoin solutions to other kinds of equations, right?
Yeah, but this one, just to decide. Yeah.
So you just selected this class of equations that you have to look for completion of a system.
Yeah. So as I understand it, you're saying that in principle, just for any old equation, even if it's not one of this kind, I could still somehow look at a smaller subring,
yes,
over which it becomes integrable. Yeah. And I think in principle that should be interesting, but these two examples are very, very special. This is a lot easier to control than just talking about the field where it becomes integrable.
Meaning it's easier to get results there, or that's what this means?
I think it's easier to get results there because I can describe what's happening. With the other ones, it might have to be a special situation. Okay, so let me kind of briefly walk you through the ideas in the proof. We start from this result of Schaefke saying that in either the shift, periodization, or Mahler situations, if you're given a difference equation over C of x, then it's actually gauge equivalent to a difference equation with constant coefficients. And yeah, this is a big deal. This is kind of amazing. Yeah.
Is it possible to say half a sentence for gauge equivalent fields?
Yes, I can also write something down.
What was the question?
What does gauge equivalence mean?
Gauge equivalence.
Yeah. So
he wrote the formula.
So let me say these are gauge equivalent. Let me say. If B is equal to sigma of A, oh no, right. Sorry. Sigma of T, A T inverse for some T.
Oh, I see. Okay.
Yeah.
Okay.
So there's a definition, and the definition is designed to make it so that if you act on if you define y to be t of z or z to be t times y, this is how the equations are conformed. Okay. But in particular, the Picard-Bessel extension and the Galois group for gauge equivalent systems are the same, not just like literally equal.
Carlos,
Yes.
is K there C of T? Is it the same? Or is it
Sure.
something-
This is what it needs to be gauge equivalent over any K. But
Oh, okay.
but I'm thinking of CFT, and that's actually important here. The gauge transformation actually lives in the rational functions, even in the Mahler case where you have a log hanging around. Okay. So once you know this, here's how the proof of the previous result goes. So first you show that the difference Galois group for a constant system has to be abelian. And so now the same is true for an integrable system because any integrable system is equivalent to a constant one. So now we have the result for integrable systems. If it's only projectively integrable, there's a way to there's a linear algebra construction that allows you to get rid of the effect of the determinant. Use Kronecker products and some stuff, and you can produce explicitly a higher order system whose Galois group is integrable, and so that the Galois group you do care about sits in this kind of exact sequence. And I know that this bigger system lives in GLN to the n of the same base field. So now I can apply this result again and say that S tilde has to be abelian, this is abelian, so X is forced to be solvable. Then we do quite a bit more work to actually write down what the groups have to look like. These are the results for the difference group, but then the differential group. Oh, I'm sorry. Yeah, I just said that. And the differential group. So we're sitting inside the difference group. So it's still solvable in this. Solvable in this case, and abelian in this case.
Is it Zariski dense in the sigma group?
Yes.
Yeah.
I don't know if I mentioned before. In this theory, the difference differential group is always Zariski dense in the difference group. So let me have some more time. Let me say what the groups look like. It's not just that they're abelian or solvable. In the shift case, the difference group always looks like that, and the Q dilation and Mahler is similar, but so it didn't have space. This is cross Z mod T cross Z mod P, where R, S, T, P are all integers. R has to be non-negative. S is either 0 or 1, and T and P are positive. So they're not just abelian, they all look like that.
C prime.
Pardon me?
C prime.
Is what prime?
Prime now?
Oh, no, it's just a normal P. And yeah, so the only thing special here is really the control on the number of connected components and the control on the uniform radical. But that's a content here. Once you know that it's abelian. And I should also say that in the projectively integrable setting, where you only know that they're solvable, they're like usually they're actually abelian too. So let me just say that in the projectively integrable thing, this is abelian if the common GCD of n being the order of the equation and this T and P is equal to 1. So this is enough to guarantee that it's actually abelian. Okay. So in the spirit of the workshop, I wanted to mention some things that are still left to be done. So these results allow you to say a lot about the differential structure of the solutions to your equation once you know something about the algebraic structure. So for this to be useful, you need to know how to compute the classical differentiality. And this has been done in some special cases. Feng has a Khrushchevsky-style algorithm for shift difference equations over the rational functions. Then between Hendricks and Rock, they've done the analog of Kovačik's algorithm for difference algebra in multiple cases, shift, utilization, and Mahler. And it would be interesting to have more general algorithms in these other two cases of interest. Then our results kind of advance the inverse problem of this Galois theory. But in general, you're interested in somehow knowing which differential groups do arise as difference-differential Galois groups. This is useful in algorithms because an algorithm to compute a Galois group, all the groups are there already. You just have to decide which one it is, and if you have less choices, it's easier to pick out the correct one. So this is we can say a little bit more using our results, but for example, now we know that the constant points of a semi-simple group that is not a difference-differential Galois group in any one of these cases.
You mean the base C of x?
Yeah, with the base C of x. Right, so you'd also like to, after you've done this, also have algorithms to compute difference-differential Galois groups. These are all for just the classical difference Galois groups. So I have, hopefully it will be in print soon, but I of course don't know. But I have an algorithm for second order difference equations in the shift case. And I started thinking about the Q difference and Mahler case. If you're into that, reach me by email, let's do it then. And then something else that seems sort of right now is to prove similar results to mine with Singer or Dreyfus-Hardouin and Rock for either differential or difference equations with a discrete parameter. And the reason that seems doable is that first, Schaefke and Singer have a similar result to the one I stated in this setting as well, where the sigma is not part of the equation. And there are Galois theories to handle either differential or difference equations with a discrete parameter. In the difference-difference case, where say you have like a sigma multiplying x by q and a different sigma multiplying x by x prime, that kind of situation. Alexey Ovshinnikov and Mikhail Widmer have a Galois theory where the groups are different algebraic groups in the sense of Widmer. And for differential equations where there's some sigma hiding in the background, there's also a Galois theory for those developed by Lucia Di Vizio, Charles Hardouin, and Mikhail Widmer again. And so, I think that because different algebraic groups are a little bit more complicated than the differential ones, you have to keep the Hopf algebras and the functorial set up in mind more often. I think the very similar results should hold in this setting as well. So that's all I have. Thank you very much.
Questions?
On the inverse problem, in the parameterized differential Galois theory, you can't realize the additive group of your C that's over C of X.
Right.
What about in this case? What about unipotent groups realizing families?
Yeah. So there are similar results saying what can and can't happen, but the answers are different, but the reasons are the same as in the differential setting.
Oh, okay.
So for example, in the Schaefke case, you can't get the full, any intermediate group between 0 and the full additive group as a Galois group. It's only GA of all of the differential closure or nothing.
This is the exact opposite.
Yeah.
Singer's theory.
And for the multiplicative group, you can only get the multiplicative constants or all of GM, or the finite ones. Yeah. So there are very even heavy restrictions in the setting as well that help you. And so yeah, this is a similar result, right, to the one for GA. Saying like in principle these groups should be able to occur, but they can only happen if you have integrability, and but those groups have to be abelian because of mapping.
Okay.
Questions? I'm curious, is there any hope of being able to expand this to more than one variable? Because not just C of X, but
yeah, so the Galois theories work the same in more generality. Say that you have C of X n, and sigma is shifting the n, and delta is differentiating the x. It's a Galois theory that applies well there, but this results don't hold anymore. Like there are all these results about which Galois groups can't occur. They assume that your equation, that your base field is something that C of X and sigma and delta are acting on the same thing and not separate things.
Yeah.
The results are just not true anymore when you allow.
Well, I was thinking about the case of not just one variable, but multiple variables, and letting Q act by some kind of matrix action. So that would be generalizing
Sure.
the Q business to higher dimensional unit varieties instead of elliptic curves.
Yeah, you could have any field of rational functions over your favorite difference field, and let delta only act on the x. The theory applies, but you don't know any facts about what happens out in the world. Somehow having a more interesting difference field of differential constants. That's where the interesting Galois groups would come about. Some of the equations defining them would come from things that you have living in a difference field.
Carlos, suppose you generalize in a different way and use the parameterized theory for the derivations, and then this regular sigma difference theory. I was thinking, for example, of the incomplete gamma function. I'm trying to see what all the differential algebraic different subfields are. That has gamma satisfies incomplete as well as complete satisfies a difference equation, and differential equations with respect to partial t and partial x, the upper limit. Have you looked at all at that case? I was wondering what that Galois theory would look like.
So Galois theory for so the incomplete gamma functions say
Yes.
it does satisfy the dx equation, but not the dt equations. And
It satisfies dx and dt.
But it's dt transcendental.
It's a parametrized theory, and the gamma generates the parametrized P-Carvesio extension.
Right.
And so gamma is a solution of partial differential equation, as well as the linear one with respect to partial x. And so that if you look at, if delta is partial x, partial t, then a question I ask myself is, if you go through the NIST handbook of special functions and look at the incomplete functions, special functions that are related in some way to the incomplete gamma function, would be interesting to know which ones you capture as invariants of the various subgroups of the Galois group. So that it would be nice to have a combined theory of the difference equation for incomplete gamma and the partial differential equations.
So
I think that's
the single-head one theory handles compatible systems of difference-differential equations where the parameters are all differential.
right, yeah.
I don't know to what extent it might be possible to combine, like maybe have one discrete parameter and some differentials.
Yeah, keep the
the-
difference theory the same, exactly the same. And then you'll be in the classical case of NIST. But change take the full description of incomplete gamma as a solution of partial differential equation over CMAX.
Yeah. Now that was, I have a paper on the complete gamma function being DDT transcendental, but
Oh, okay.
even though it satisfies this DX equation.
Thank you.
I wasn't aware that it also satisfies a difference equation, the incomplete gamma function.
Yes, it's
Okay.
look at the new handbook
Okay.
from the Bureau of Standards.
I left it
Big
off.
and red with a beautiful picture of Newton's cottage.
Okay.
With a
Everyone
superhuman
go out and get
wearing
this book.
rainbow over the top.
Other questions?
Now, it's lunchtime. We're going to start again at 1:15. And what we found last time is if you go out to Lexington, it's